a single star is caught in the tightest orbit ever observed, swinging around the black hole at the center of our galaxy at 8% of the speed of light. Nothing else ever tracked survives an orbit that close to something that massive. That black hole has no surface and gives off no light of its own, yet it holds a mass equal to about 4.3 million suns, compressed into a region smaller than the orbit of Mercury. Astronomers call it Sagittarius A star, and they found the star orbiting it, catalogued only as S471 the only way they could, by watching a faint dot of infrared light for years, tracking it as it swung around a patch of sky that looked, to every instrument before theirs, completely empty. That single measurement, taken from a point of light 26,000 light-years away, is some of the strongest evidence that gravity behaves exactly as Einstein's equations predicted, even in the one place physicists once assumed those equations would simply break down. In 1932, an engineer at Bell Telephone Laboratories named Karl Jansky was trying to solve a much smaller problem: static that kept interrupting transatlantic radio calls. He built a rotating antenna to hunt down the source and found 3 kinds of noise. 2 were storms nearby and distant. The third rose and fell on a rhythm that matched the stars rather than the clock, and it came from one direction more strongly than any other, toward the constellation Sagittarius, toward the crowded heart of our own galaxy. Jansky had no way to know it, but he had just detected radio waves pouring out of the center of the Milky Way, decades before anyone understood what could produce them. A few years later, an amateur radio engineer named Grota Rieber picked up where Jansky left off, building a homemade radio dish in his backyard in Illinois, and drawing the first crude maps of the sky in radio light rather than visible light. The picture that slowly came into focus showed the galactic center as one of the brightest radio sources in the sky, far brighter than any single star could explain. Optical telescopes were useless here. Thick clouds of interstellar dust block almost all of the visible light coming from the galaxy's core, which is why, on even the clearest night, no telescope on Earth can simply look at the center of the Milky Way and see anything there at all. Radio waves and, later, infrared light pass through that dust far more easily, and it was through those wavelengths that astronomers would eventually see what visible light could not. It took until 1974 for the picture to sharpen into something specific. Using a radio interferometer, a technique that combines signals from separated antennas to achieve the resolving power of a single, much larger dish, astronomers Bruce Ballack and Robert Brown identified a compact, essentially unmoving source of radio emission sitting at the dynamical center of the galaxy. It was small, intense, and did not behave like an ordinary cloud of gas or a supernova remnant. They named it Sagittarius A star, marking it as the standout component within the broader Sagittarius A region, a name that has stuck ever since as shorthand for the object at the very center of the Milky Way. What Sagittarius A star actually was remained an open question for another 2 decades. A compact radio source is not proof of a black hole. It could, in principle, be a dense cluster of ordinary stars or some other kind of exotic remnant. Radio emission alone could not settle it. What was needed was a way to weigh the thing directly, and the only reliable way to weigh an object in space is to watch something orbit it and measure how fast it moves. That meant finding stars close enough to the galactic center to feel its gravity strongly, and tracking their motion patiently enough and precisely enough to calculate a mass. The dust that had hidden the galactic center from visible light telescopes for half a century was thinner in infrared light, and by the early 1990s, telescope technology had finally caught up to the problem. A new generation of large ground-based telescopes, paired with adaptive optic systems that could correct for the blurring of Earth's atmosphere in real time, made it possible, for the first time, to resolve individual stars swarming around whatever it was that radio astronomers had found. 2 teams took up the challenge almost simultaneously, one led by Andrea Ghez, using the Keck Observatory in Hawaii, the other by Reinhard Genzel, using the European Southern Observatory's telescopes in Chile. Both groups began doing something that sounds almost absurdly patient by the standards of modern astronomy: photographing the same small patch of sky year after year and marking the position of every star bright enough to see. Most of those stars barely moved at all across the frame, the way distant background stars should. A handful did not behave that way. They shifted position from one year's image to the next by amounts too large to be anything but real, physical motion, tracing out looping paths across the sky the way a swarm of insects circles a bright porch light. Those few fast-moving stars became the entire foundation of everything that would follow. Each one was in effect a test mass, a probe placed by nature into the gravitational field of whatever sat at the center of those loops, doing the work that no spacecraft could safely do. The astronomers did not need to see the massive object directly. They only needed to watch its influence written into the motion of stars nearby, the same way a ship's wake can be traced back to a vessel hidden by fog. What those loops would eventually reveal, once enough years of data accumulated, was a mass so large and so compact that no ordinary explanation could account for it, and a single star's orbit would turn out to be the sharpest tool anyone had for measuring it. A single photograph of a moving star tells an astronomer almost nothing. A star's true orbit is a three-dimensional path traced out over years, and from the ground, all that can be measured directly is its position projected flat against the sky, plus, with the right instrument, the small shift in its light that reveals motion straight toward or away from Earth. Reconstructing a real orbit from that limited information meant collecting images across many years and fitting a mathematical curve to the pattern of dots, refining the fit every time a new observing season added another data point. It was slow, unglamorous work, closer to bookkeeping than to the popular image of astronomical discovery, and it went on for the better part of 2 decades. One star, catalogued as S2, stood out early as the best candidate for this kind of long, patient study. It was bright enough to track reliably, and close enough to the center to complete an orbit on a human timescale rather than a geological one. As more years of data accumulated, its path resolved into an unmistakable ellipse, tight at one end and wide at the other, the signature shape of any object bound in orbit by gravity, rather than drifting freely through space. That shape mattered enormously, because a closed elliptical orbit is exactly what Johannes Kepler described 4 centuries ago, when he worked out the laws governing how planets move around the Sun, laws that still apply unmodified to any 2 bodies bound by gravity anywhere in the universe. Kepler's third law connects an orbit's size and period directly to the mass of the object being orbited. Feed in how long S2 takes to complete one full loop and how far it travels at its widest point, and the equation returns a number for the mass sitting at the empty-looking focus of that ellipse. When both rival teams ran the calculation independently, using different telescopes, different instruments, and different analysis methods, they arrived at strikingly similar answers. Something with roughly 4 million times the mass of the Sun was concentrated at that single point in space. That figure, checked and rechecked against every new year of tracking data, has held up for 3 decades now, refined slightly but never overturned. A mass that large is already remarkable, but the mass alone was not what closed the case for a black hole. What sealed it was combining the mass with the volume the tracked stars proved it must occupy. If 4 million solar masses were spread across a region, even a modest fraction of a light-year wide, spanning roughly the distance light travels in a year, ordinary explanations, a dense star cluster or an unusual gas cloud, would still be viable. But the orbits of the fastest stars swung so close to the center and moved so quickly as they did that the mass had to be packed into a region smaller than the distance from the Sun to its nearest planets. There is no known configuration of ordinary matter, no cluster of stars or cloud of gas, that can be compressed that tightly without collapsing further under its own gravity. Compressed past a certain density, matter has nowhere left to go but inward, all the way down to a black hole, a region where gravity has become so strong that nothing, not even light, can climb back out once it crosses the boundary. So by the early 2000s, the case had shifted from suggestive to essentially undeniable. Sagittarius A star was not merely a bright radio source anymore. It was a supermassive black hole, 4 million times heavier than the Sun, sitting at the exact center of the galaxy that contains our own solar system, our Sun, and the Earth beneath your feet, all of it orbiting that distant, invisible anchor once every few 100 million years, the way every star in the Milky Way's disk does. The scale of that realization is easy to state and hard to actually feel. An object with no surface and no light of its own was quietly governing the motion of hundreds of billions of stars, and had been doing so since long before anything resembling human existed to measure it. S2 itself had one more chapter left to write. Its orbit was long, close to 16 years, to complete a single loop, which meant that decades of patient tracking were building toward a single unrepeatable moment, the point in that orbit where the star would swing closest to the black hole and move fastest, the moment when gravity's effects on light, time, and the star's own path would be strongest and most measurable. Both observing teams knew the date of that closest approach years in advance, the way an astronomer can predict an eclipse, and they spent that time preparing every instrument they had for the single pass that was coming. S2 completes one full circuit of the black hole roughly every 16 years, which is itself a strange thing to sit with. A star with a lifespan of millions of years, tracing out an orbit whose single lap takes about as long as a human childhood. For most of that orbit, S2 drifts leisurely, far enough from the black hole that gravity there behaves in the ordinary, well understood way it does anywhere else. But an elliptical orbit is not a circle. At one point along its path, S2 swings dramatically closer, diving into a distance of roughly 17 light hours from the black hole, a little farther than the distance from the Sun to the planet Neptune, before swinging back out again. In May 2018, S2 reached that closest point, and for the first time, astronomers were ready with instruments precise enough to catch what happens to a star at the edge of a black hole's grip. What they were watching for was a specific prediction of Einstein's general relativity called gravitational redshift. Light climbing out of a strong gravitational field loses energy as it escapes, and losing energy stretches its wavelength toward the red end of the spectrum the way a ball thrown upward loses speed as it climbs. Near an ordinary star like the Sun, this effect is real but tiny, far too small to notice without extraordinarily sensitive instruments. Near a supermassive black hole, at a distance where a star is moving at several % of the speed of light, the effect becomes large enough to measure directly, and Einstein's equations predict a specific, calculable amount of stretching, no more and no less. Newton's older theory of gravity, the one that describes falling apples and orbiting planets perfectly well, almost everywhere else in the universe predicts no such stretching at all. Using an instrument called gravity, built specifically for this kind of measurement and mounted on the European Southern Observatories, Very Large Telescope in Chile, an international collaboration tracked S2's light through its 2018 closest approach with a level of precision that had never before been achieved for any star this far from Earth. The result matched Einstein, not Newton. S2's light stretched by exactly the amount general relativity predicted for an object of that mass and that closest distance, and no more. It was the most extreme environment in which gravitational redshift had ever been directly measured. A test performed 26,000 light-years from Earth, on an object no human instrument could ever visit or touch. 2 years later, the same collaboration announced a second confirmation, this time of an effect called Schwarzschild precession, named for the physicist who first solved Einstein's equations for the gravity around a compact spherical mass. In an ordinary orbit governed by Newtonian gravity, an ellipse traces the same fixed path over and over, forever. Near a sufficiently massive, sufficiently compact object, general relativity predicts something subtly different. The whole ellipse itself should slowly rotate, so that the point of closest approach shifts a little further around each time, tracing out a shape closer to a rosette than a simple oval drawn over successive orbits rather than one. This is the same relativistic effect that first confirmed general relativity back in 1915, when Einstein used it to explain a long-standing puzzle in the orbit of the planet Mercury, whose closest point to the Sun drifts slightly with each orbit in a way Newton's gravity alone could never fully explain. A century later, the same signature turned up again, at a vastly larger scale, in the orbit of a star around a black hole 4 million times the Sun's mass. In 2020, the Nobel Prize in Physics recognized this decades-long effort. Reinhard Genzel and Andrea Ghez shared half the prize for their observational discovery of the supermassive compact object at the center of our galaxy, the culmination of the very tracking campaigns described a chapter ago. The other half went to the mathematician and physicist Roger Penrose for showing decades earlier, through pure theoretical reasoning rather than observation, that black holes are not an exotic special case, but a robust and unavoidable prediction of general relativity itself, wherever enough mass is compressed into a small enough space. One half of the prize honoured the theory that said black holes must exist. The other half honoured the patient, decades-long measurement that found one, sitting at the centre of our own galaxy, and used a single star's orbit to prove it. S2's 2018 closest approach was a triumph, but it was not the closest anything gets to the black hole. Even as that measurement was being finalised, astronomers had already spent years mapping a much denser, much more chaotic region of space immediately around Sagittarius A star, a swarm of stars now known collectively as the S cluster. S2 belongs to this group, but it is far from the most extreme member. Squeezed into a region of sky roughly the size a coin held at arm's length would cover, the S-cluster contains dozens of individually tracked stars, each looping around the black hole on its own tilted, stretched-out orbit at distances and speeds that make S2's own extreme orbit look almost restrained by comparison. Finding and confirming a new S-cluster member is exacting work. The stars are faint, packed close together on the sky, and buried in the glare of scattered light from the black hole's immediate surroundings. Astronomers using an instrument called Symphony, a spectrograph mounted on the Very Large Telescope, separated starlight from that glare by splitting it into its component wavelengths, and looking for the specific spectral fingerprint that identifies a single hot, young star rather than a smear of background light. Doing that patiently, image after image, year after year, an international team led by astronomers at the University of Cologne confirmed a handful of new S-cluster members through the 2010s and into the 2020s, each one adding another test mass to the gravitational map of the region. One of those stars, catalogued as S471, turned out to be extraordinary even by the S-cluster's already extreme standards. Its orbit is so elongated, so far from a simple circle, that at its widest point it drifts out to a leisurely distance comparable to other S-cluster stars, but at its narrowest point it plunges in dramatically closer than S2 ever gets, passing within a region smaller than the distance separating the outer planets of our own solar system. The orbit completes in roughly 12 years, shorter than S2's 16, which on its own would have made S4714 notable. What made it remarkable was the sheer eccentricity of that path, measured on a scale from a perfect circle to an almost impossibly stretched sliver of an ellipse. S4714's orbit sits closer to the stretched extreme than almost any bound orbit ever confirmed around any object anywhere. An orbit shaped like that behaves nothing like the gentle, near-circular paths planets trace around the Sun. For most of its 12-year lap, S4714 drifts slowly through the outer reaches of its path, moving at speeds not drastically different from other S-cluster stars. Then, over a span of days rather than years, it falls inward, accelerating the entire way until it whips around the black hole at its closest point and rockets back outward, the whole close encounter compressed into a brief violent pulse within an otherwise unhurried orbit. It is the orbital equivalent of a pendulum that spends most of its swing barely moving, and then, for one instant at the bottom of its arc, moves faster than anything else in the room. What happens during that brief pulse is the reason S4714 matters at all. A star's speed at its closest approach depends entirely on how deep into the black hole's gravity it has fallen, and how tightly its path curves there, and S4714's geometry meant its closest approach would be deeper and tighter than any previously confirmed stellar orbit around Sagittarius A star. When the team calculated that peak velocity from the orbit is measured shape and period, the number that came out was not a few percent of the speed of light, the range S2 reaches. It was close to 8%, a speed high enough that the ordinary language used to describe planetary motion starts to feel inadequate, and language borrowed from particle physics, where speeds are routinely discussed as fractions of light speed, becomes the more natural way to talk about it. 8% of the speed of light works out to roughly 24,000 kilometers per second. That number is difficult to hold in the mind honestly, because nothing in ordinary experience moves anywhere close to it. A rifle bullet travels at roughly 1 kilometer per second. The fastest spacecraft ever launched by humans, sent on a trajectory that used the Sun's own gravity as a slingshot, topped out at around 190 kilometers per second, a genuine engineering triumph and still more than 100 times slower than S471T at its closest approach. At 24,000 kilometers per second, a star could cross the entire continental United States, coast to coast, in under 0.2 of a second. It could circle the entire Earth roughly 6 times in the space of a single second. These comparisons are not meant to be precise. They are meant to make an abstract number feel physically real, because a speed this extreme genuinely is real, measured on an object 26,000 light-years away, using nothing but the shift and timing of its own faint light. What makes a speed like that possible is not some property of the star itself, but simple, brutal gravity. The closer any orbiting body gets to a massive object, the faster it must move to avoid falling straight in, the same reason a skateboarder speeds up at the bottom of a steep bowl and slows again climbing the far side. S4740's closest approach brings it into a region of space where the black hole's gravity is overwhelmingly stronger than anything a star ever experiences in an ordinary stellar environment, and the star's orbital speed simply reflects how strong that gravity has become. There is nothing exotic about the star producing this speed on its own. The black hole is doing all the work, and the star is simply falling as fast as the geometry of its own orbit demands. A speed this extreme has consequences for the star itself, and for how astronomers even measure it. Special relativity, the part of Einstein's physics dealing with objects moving at a significant fraction of the speed of light, predicts that time passes more slowly, from an outside observer's point of view, for anything moving that fast. During the brief days when S471 is near its closest approach, moving at 8% of light speed, its own internal clock, if it somehow had one, would tick very slightly slower than a clock sitting safely far away. The effect at 8% of light speed is small, a matter of a fraction of a percent, but it is not zero, and any calculation of the star's orbit that ignored it would drift out of agreement with what astronomers actually observe. General relativity adds a second, independent slowing on top of that, caused not by speed but by the sheer strength of gravity so close to the black hole, the same effect confirmed directly in S2's gravitational redshift. Near S4714's closest approach, both effects act together, and disentangling exactly how much of the total slowdown comes from speed, and how much from gravity is itself one of the reasons this star is such a valuable natural laboratory. None of this means S474 is being torn apart by the encounter, at least not yet, and that fact turns out to matter as much as the speed itself. A star can survive a close pass around a black hole only if the black hole's gravity does not differ too dramatically between the near side of the star and the far side, a difference called a tidal force. Too large a difference stretches a star apart, the way the moon's much gentler tidal pull raises ocean tides on Earth, except strong enough here to eventually shred the star into a stream of gas. S4740's closest approach is tight, but the black hole's enormous mass is also spread across an enormous region compared to the star's own small size, which keeps the tidal difference across the star's diameter survivable, at least for now. The star pays for its speed only in the strange currency of time, stretched and compressed by both velocity and gravity, and comes back out the other side of its closest approach still whole, ready to drift back out to the leisurely far side of its 12-year orbit before falling in again. There is something odd about S4714 that has nothing to do with its speed. Spectroscopic measurements, the same technique used to detect the star in the first place, show it to be young and hot, a blue-white star still burning through the early stages of its life. Not the faded, aged star an astronomer might expect to find surviving in such a punishing neighborhood. Most of the S-cluster's confirmed members share this trait. They are, almost without exception, young massive stars, the stellar equivalent of finding an unusually concentrated group of teenagers living permanently in one of the most hostile environments imaginable. That observation, first noticed among S-cluster stars generally, and repeated with each new discovery, became known among astronomers as the paradox of youth, and it remains only partly resolved. The paradox is straightforward to state. Stars form when a large cold cloud of gas and dust collapses under its own gravity, slowly gathering enough mass and pressure at its center to ignite nuclear fusion. That collapse is a gentle, patient process, one that unfolds over hundreds of thousands of years, and it requires a gas cloud stable enough to hold together throughout. Anywhere within a light year or so of a black hole as massive as Sagittarius A star, gravity from the black hole itself should overwhelm a forming cloud's own weak self-gravity long before it could collapse into a star, stretching and shredding the cloud apart in what astronomers call a tidal disruption, the same fate a star can eventually suffer if it strays too close once it already exists. By every straightforward model of star formation, no star should be able to form within the S-cluster's crowded inner region at all, and yet there they are, dozens of them, unmistakably young. Several explanations have been proposed, and none of them has yet been confirmed beyond reasonable doubt, which is itself an honest and useful thing to say about an active area of research. One idea holds that these stars did not form where they now orbit, but were born much farther out, in a region where gas clouds could collapse safely, and were later dragged inward over millions of years by gravitational interactions with other stars and gas structures, a slow migration rather than an in situ birth. Second idea proposes that a dense, short-lived disk of gas once existed in a stable orbit close to the black hole. thick and cold enough in patches to collapse locally into stars despite the black hole's tidal pull, a scenario with some observational support from a separate, somewhat older population of stars found orbiting slightly farther out in an actual, still visible disk-like arrangement. A third, more exotic possibility suggests some S-cluster stars might not be single stars at all originally, but the surviving product of two stars merging after being gravitationally forced together, a violent stellar collision that could reset a star's apparent age and composition, and make an old star look deceptively young. Whichever explanation eventually wins out, or however the truth turns out to be some combination of all three, the puzzle highlights something important about the region S4714 calls home. It is not simply an empty gravitational field with one lonely star looping through it. It is an active, crowded, still poorly understood astrophysical environment, shaped by forces astronomers are still working to fully characterize. Gas dynamics, stellar collisions, and slow gravitational shepherding, all happening in the extreme gravity well of a supermassive black hole. S471 is not an isolated curiosity. It is one visible thread in a much larger, tangled story about how matter behaves and how stars can, against considerable odds, still manage to exist in the most gravitationally violent neighborhood in the entire galaxy. That unresolved history matters for another reason too. Understanding how S4714 came to be where it is affects how confidently astronomers can predict what will eventually happen to it, and to the black hole's other close stellar neighbors, over the much longer timescales still to come. Every measurement of Sagittarius A star has come second-hand. No telescope has ever photographed its surface because it has no surface and no light escapes from close enough to it to be gathered by any camera. What astronomers know about the object itself comes entirely from watching what it does to things around it. A star's orbit, a stream of hot gas spiraling inward, or the faint glow of matter just outside the point of no return. It is worth being precise about what that point of no return actually is, because the popular image of a black hole as a hole in space, sucking matter toward it like a drain, gets the physics wrong in an important way. A black hole's defining boundary is called the event horizon, and it is best understood not as a physical surface, but as the edge of a region where gravity has become strong enough that the escape velocity, the speed something would need to break free, exceeds the speed of light itself. Outside that boundary, gravity behaves exactly as it does around any other massive object. An object with the same mass as Sagittarius A star, spread out however you like, would pull on a distant star or planet with exactly the same force, following the same laws that govern the Earth's orbit around the Sun. If the Sun itself were somehow replaced by a black hole of the same mass, Earth's orbit would continue completely unaffected, because nothing about gravity outside the horizon changes just because the mass has become compact. What changes is only what happens once something crosses that boundary. Past the event horizon, and only past it, the equations of general relativity say that nothing, not light, not matter, not any signal of any kind, can find a path back out. For an object with a mass of about 4.3 million suns, the mathematics of general relativity gives an exact size for that boundary, a distance called the Schwarzschild radius, named for the physicist whose solution first described it. Sagittarius A star's event horizon works out to a boundary roughly 12.7 million kilometers from the black hole's center, meaning the entire event horizon, edge to edge, spans somewhere around 25 million kilometers, a little over 18 times the diameter of the Sun. Hold those two numbers side by side and the strangeness comes into focus. An object with 4 million times the mass of the Sun fits inside a region only about 18 times wider than the Sun itself. That combination of enormous mass and comparatively modest size is precisely what makes a black hole, and precisely what makes it invisible to direct observation. There is no surface glowing with starlight to see, only the mathematically precise edge of a region that swallows light rather than reflecting it. Because nothing escapes past that boundary, the event horizon itself can never be photographed directly, only inferred by its effect on light and matter that pass near it, but stay outside it. This is exactly the same principle that made tracking S2 and S4714 necessary in the first place. Astronomers cannot see the black hole, so they watch what orbits it instead, the same way a shape in deep fog can be inferred from the paths of birds flying carefully around it. A star's orbit reveals the black hole's mass. The bending, stretching, and dimming of light passing near the horizon reveals its size and shape. Every fact known about Sagittarius A star, including the number 4 million and the number 18, has been assembled entirely from these second-hand signatures, never from a direct view of the object itself. What makes this particular black hole special is not that it is unusually large. Supermassive black holes elsewhere in the universe reach billions of solar masses, hundreds of times heavier than Sagittarius A star. What makes it special is proximity. At 26,000 light-years away, it is by a wide margin the closest supermassive black hole to Earth, and its comparatively modest mass paired with that closeness gives it, from our vantage point, an apparent size on the sky larger than almost any other black hole astronomers have ever tried to study, making it the single best natural laboratory available anywhere for testing what gravity actually does at its most extreme. Step back from any single star, and the last several decades of observation around Sagittarius A star amount to something larger than a catalogue of individually impressive discoveries. They amount to a working experiment conducted not in a laboratory, but across 26,000 light-years of empty space, testing whether Einstein's century-old description of gravity still holds up in the most extreme gravitational environment anywhere near our own galaxy. Isaac Newton's gravity, formulated more than 3 centuries ago, describes the pull between two masses with extraordinary accuracy almost everywhere astronomers have ever tested it. Spacecraft trajectories, planetary orbits, the paths of comets. But Newton's equations were built from observations made entirely in comparatively weak gravitational fields, nothing remotely close to the environment near a supermassive black hole's event horizon. General relativity was the first theory to predict, in detail, exactly how gravity should behave when it becomes that strong, and until stars like S2 and S471 could be tracked precisely enough, nobody had a way to check those predictions directly. 3 specific predictions have now been tested using these orbits, and general relativity has passed each one. The first is gravitational redshift, confirmed using S2's 2018 closest approach. Light climbing out of a strong gravitational field loses energy and stretches toward the red end of the spectrum by a precise calculable amount, and S2's light did exactly that, matching Einstein's prediction rather than Newton's, which predicts no such stretching at all. The second is Schwarzschild precession, confirmed 2 years later using the same star. Rather than tracing the same fixed ellipse forever, S2's orbit itself slowly rotates, shifting its point of closest approach a little further around the black hole with each successive lap, exactly the effect general relativity predicts and Newtonian gravity cannot produce. The third, still being refined using stars including S4714, involves the combined effects of relativistic time dilation, both the kind caused by extreme speed and the kind caused by extreme gravity, on exactly how a star's light and position appear to observers watching from Earth. What makes this body of evidence unusually convincing, compared to many results in astrophysics, is that it does not rely on a single measurement or a single instrument. 2 independent observing teams, using different telescopes and different methods, derived the same black hole mass from S2's orbit years before either relativistic effect was tested. A separate, later collaboration measured the gravitational redshift using purpose-built instrumentation designed specifically to catch that one effect, during that one unrepeatable closest approach. Newly discovered stars like S471Phi, found through an entirely different survey technique years afterward, extend the same basic test into an even more extreme regime, at even greater speeds and even smaller distances, and so far every new data point has continued to agree with Einstein's predictions rather than contradicting them. A theory that fails even one such test would be in serious trouble. General relativity has now passed several, conducted independently, at the edge of an actual black hole. None of this means physicists consider general relativity a finished, complete theory of gravity. It is famously incompatible, in a deep mathematical sense, with quantum mechanics, the theory that governs matter at the smallest scales, and reconciling the two remains one of the largest open problems in all of physics. What these measurements around Sagittarius A star do confirm is narrower but still profound. In the specific extreme regime near a supermassive black hole's event horizon, general relativity's predictions continue to hold, at least within the precision current instruments can achieve. Every improvement in telescope sensitivity, every newly discovered star orbiting a little closer, or moving a little faster than the last, gives physicists another chance to look for the crack that would finally show general relativity's limits. So far, orbiting stars keep declining to provide one, and each star that keeps agreeing with the theory adds one more small, hard-won piece of confidence that humanity's best description of gravity, worked out entirely on a chalkboard more than a century ago, really does describe the universe accurately. Even here, at the edge of an object light itself cannot escape. Every measurement of Sagittarius A star up to this point had been indirect, inferred from the motion of stars rather than seen with any camera. In May 2022, that changed, at least partially. A global collaboration called the Event Horizon Telescope, linking radio dishes on mountaintops and in deserts across multiple continents into a single, Earth-sized virtual instrument through a technique called Very Long Baseline Interferometry, released the first direct image built from light gathered at the very edge of Sagittarius A star. It was not, and could not be, a photograph of the black hole itself, since a true black hole emits no light to photograph. What it showed instead was a shadow, a dark, roughly circular region where the black hole blocks and bends light from hot glowing gas swirling in its immediate surroundings, ringed by a faint uneven halo of that same glowing gas, warped and bent by gravity so extreme that light itself is forced to curve around it. The project had already produced one such image 3 years earlier in 2019, of a different, far more massive black hole at the centre of a galaxy called M87, roughly 55 million light-years away. That black hole is enormous, weighing in at something like 6.5 billion suns, more than 1,000 times heavier than Sagittarius A star. What makes the two images comparable at all, despite that enormous difference in mass, is a coincidence of distance. M87's black hole is vastly more massive but also vastly farther away, while Sagittarius A star is comparatively modest in mass but sits far closer to Earth, and the two effects roughly cancel out, leaving both black holes appearing at almost the same apparent size when viewed from our particular vantage point in the universe. It made Sagittarius A star the second, and much closer, target for the same technique, though imaging it turned out to be considerably harder. The difficulty came down to speed. Because Sagittarius A star is so much smaller than M87's black hole, hot gas near its edge completes an entire orbit in a matter of minutes rather than days or weeks, meaning the gas structure the telescope was trying to photograph was changing shape while the observations were still being collected, the equivalent of trying to take a single sharp photograph of a hummingbird's wings using an exposure time far too long for how fast they beat. Untangling a stable average image out of that constantly shifting pattern required years of additional data processing and cross-checking after the raw observations were gathered, which is why the image, despite using data collected around the same time as the M87 result, was not released until 3 years later. When the image finally emerged, its size matched almost exactly the size long predicted from decades of entirely separate evidence. The mass calculated from S2's orbit, the boundary size calculated from that mass using general relativity's equations, all converging on the same answer that the direct image now confirmed visually. It is rare, in any branch of science, to have a result checked by two such completely independent methods, one built from years of tracking a star's position across the sky, the other built from combining radio signals gathered simultaneously from telescopes spread across the entire planet, and to have both methods agree this precisely. The image did not overturn anything the star tracking measurements had already established. It confirmed it, visually, for the first time, turning decades of careful indirect inference into something that finally, if only in a narrow technical sense, could be called a picture. What the image could not do, and what no image built from light near the horizon will ever be able to do, is show anything at all about what lies past that boundary. The shadow marks an edge. What lies on the far side of that edge is where the honest limits of observation begin, and where general relativity's own equations start making stranger and harder to verify predictions. The star's orbit, the redshifted light, the shadow imaged in 2022. Each describes the region outside Sagittarius A star's event horizon, the only region any observation of any kind will ever be able to reach. What lies past that boundary is, by the very definition of an event horizon, permanently cut off from any signal that could ever reach an outside observer. That makes the interior of a black hole one of the very few places in physics where the honest answer to a natural question, what is actually in there, is that nobody knows, and nobody using electromagnetic observation ever will. What can be said comes entirely from mathematics rather than observation. Solve Einstein's equations for a black hole exactly, the same solution that gives the Schwarzschild radius used to calculate the event horizon size, and follow the geometry inward past the horizon, and the equations predict something extreme. All of the black hole's mass compressed into a point of zero size and infinite density, a location physicists call a singularity. At a singularity, the equations of general relativity stop producing sensible answers. Curvature, density, and other quantities that should have finite values instead blow up toward infinity, which is usually, in physics, a strong signal that the theory being used has been pushed past the point where it can be trusted, rather than a signal that infinity is a real physical thing. Most physicists working in this area take that signal seriously. General relativity is a theory built entirely around gravity and the large-scale geometry of space and time, and it contains no description whatsoever of quantum mechanics, the separate and equally well-tested theory that governs how matter and energy behave at extremely small scales. Compress enough mass into a small enough region, and at some point, long before reaching an actual mathematical point of zero size, quantum effects should become important in ways general relativity simply has no tools to describe. The expectation, widely shared though not yet confirmed, is that the true physical description of a black hole's innermost region requires a theory that successfully merges gravity with quantum mechanics, something physicists call quantum gravity, and no complete, experimentally confirmed version of that theory exists yet. The singularity predicted by general relativity alone is very likely a sign of where the theory runs out, not a description of literal, physical infinite density sitting at the center of every black hole. This honest uncertainty connects back in a satisfying way to Roger Penrose's half of the 2020 Nobel Prize. What Penrose actually proved decades before any black hole had been directly observed was not that singularities are physically real in every literal sense, but that general relativity's own equations robustly predict them, under very general and physically reasonable conditions, whenever enough matter collapses inward without anything to stop it. That was itself a landmark result, because it showed black holes were not some contrived edge case requiring artificial assumptions, but an essentially unavoidable consequence of the theory once enough mass collapses together. Exactly the process that likely built Sagittarius A* and every other supermassive black hole from far smaller beginnings over billions of years. Penrose's mathematics said a black hole's interior must contain something the theory itself cannot fully describe. The observational discoveries confirmed that objects matching every external prediction of that mathematics really do exist. What sits at the very center of one remains, for now, one of the genuinely open questions at the frontier of physics, and honestly saying so is more scientifically responsible than pretending otherwise. What is not in question, regardless of how the singularity puzzle eventually resolves, is what happens to anything, a star, a gas cloud, a spacecraft, that crosses the event horizon itself. Once inside that boundary, every possible future path, in the strange geometry general relativity describes there, leads only further inward, toward whatever the true center turns out to be. There is no orbit possible inside an event horizon, no stable path, no way back out regardless of speed, thrust, or any conceivable technology. It is the one genuinely absolute one-way boundary known anywhere in physics, and it is also precisely why S4714's orbit, no matter how extreme, remains, for now, entirely survivable. Every part of that 12-year loop, even its fastest, closest moment, stays safely, if narrowly, on the correct side of that line. Nothing about S4714's current orbit puts it in immediate danger, but nothing about a dense, gravitationally chaotic environment like the S-cluster stays fixed forever either. Every star in that crowded region tugs, faintly on every other, in complex gravitational interactions that slowly reshape orbits over timescales of thousands to millions of years, the same kind of gradual reshuffling that has likely already dragged some S-cluster stars closer to the black hole than their orbits started, and could just as easily nudge others farther away, or onto orbits considerably more dangerous than the one S4714 currently follows. The precise long-term fate of any single S-cluster star is difficult to predict with confidence, because it depends on the cumulative effect of countless small gravitational nudges from neighboring stars over spans of time far longer than any observing campaign has yet run. What is not speculative is what eventually happens to a star whose orbit does drift, or is nudged too close. Astronomers do not have to imagine this outcome. They have watched it happen, directly, to stars in other galaxies. Events called tidal disruptions occur when a star passes close enough to a black hole that the difference in gravitational pull between the star's near side and far side becomes strong enough to overwhelm the star's own internal gravity holding it together. Rather than being crushed inward, the star is instead stretched, elongated first into an egg shape, and then into a long thin stream of hot gas, roughly half of which is flung outward and lost to space, while the other half spirals inward toward the black hole, heating dramatically as it falls, and producing a bright flare of light that can, for a period of weeks to months, briefly outshine every other source in its host galaxy. Dozens of these events have now been caught by wide-field sky surveys designed specifically to spot exactly this kind of sudden, dramatic brightening in otherwise unremarkable, previously quiet galaxies. Sagittarius A* itself is currently a comparatively quiet black hole. It consumes gas and dust at a fairly modest rate compared to some of the far more energetic, actively feeding black holes found at the centers of other galaxies, ones that glow bright enough to outshine every star in their surroundings combined, driven by matter continuously falling in and heating to enormous temperatures on the way down. There is no known S-cluster star currently on a trajectory that would produce a tidal disruption within the near future in any timescale a human observer could witness. But the mathematics of gravitational interaction among densely packed stars suggest such an event has probably happened before, sometime in the Milky Way's long history, and will very likely happen again eventually, whether the eventual victim turns out to be S4714, S2, or some as yet undiscovered member of the same crowded cluster. A subtler, slower fate awaits stars that never suffer a dramatic tidal disruption at all. Repeated close gravitational encounters with the black hole and with other stars can gradually strip material from a star's outer layers over many orbits, or can slowly circularize an eccentric orbit like S4714's into something calmer and less extreme, or can just as easily fling a star onto a wider, wilder path entirely, even eject it from the cluster altogether on a trajectory that carries it out of the galaxy's center for good. Over the kind of timescale astronomers routinely discuss, hundreds of millions to billions of years, the entire population of stars currently making up the S-cluster will very likely look completely different from the population observed today, a slow churn of arrivals, departures, and occasional violent endings that has probably been running continuously, since not long after the black hole itself first grew large enough to dominate its surroundings. S471, in other words, is not a fixed permanent feature of the sky, any more than any other star is. It is one snapshot, caught mid-orbit, of a population still actively being shaped by the same gravity that gives its extraordinary speed. Whatever eventually happens to it, sooner or very much later, its current orbit remains one of the best natural experiments available for studying exactly the physics that will, eventually, decide its fate. It would be easy to walk away from S4714's story, thinking Sagittarius A* is some singular curiosity, a strange exception sitting at the heart of one particular galaxy. The evidence points to almost the opposite conclusion. Wherever astronomers have been able to look carefully enough, using the same basic technique of tracking the motion of stars or gas near a galaxy's center, they have found essentially the same signature, a compact invisible mass, sometimes millions and sometimes billions of times heavier than the Sun, sitting at the exact dynamical center. The Milky Way's black hole was not the first one discovered, and it will certainly not be the last. It happens, simply by virtue of galactic address, to be the closest one to Earth, and therefore the one that can be studied in the most exquisite detail. That detail is worth appreciating precisely because it is so rare. For every other suspected supermassive black hole in every other galaxy, individual stars orbiting close enough to reveal the same kind of precise, decades-long tracking data used for S2 and S4714 are simply too far away and too faint to resolve individually, even with the best instruments currently available. Astronomers studying those other black holes typically rely on cruder, statistical measurements, the overall motion of large clusters of stars, or the behavior of glowing gas disks, techniques that can pin down an approximate mass, but nothing close to the star-by-star precision achieved here. Sagittarius A*, purely because of its proximity, functions as the calibration point for the entire field, the one place where every technique can be checked directly against a known answer before being trusted anywhere else in the universe. A broader pattern has emerged from surveying many such galaxies, one that connects a central black hole's mass to properties of the entire galaxy surrounding it, not just its immediate neighborhood. Larger, more massive galaxies tend to host proportionally larger central black holes, following a fairly tight statistical relationship, first noticed in the late 1990s and confirmed repeatedly since. That relationship is surprising on its face, because a supermassive black hole, however enormous by human standards, occupies a genuinely tiny fraction of its host galaxy's total volume and mass. Sagittarius A*'s 4.3 million solar masses sounds enormous until it is compared to the Milky Way's total mass, which including its dark matter halo runs into the trillions of solar masses, making the black hole itself a rounding error by comparison. And yet somehow across galaxy after galaxy, the black hole's mass and the galaxy's broader properties track each other closely enough that most astronomers now suspect the two are not simply coincidental neighbours, but grew up together, shaping each other's evolution over billions of years through processes still being actively worked out. One piece of that shared history involves galaxy mergers. When two galaxies collide and merge, a process astronomers have directly observed happening elsewhere in the universe and expect will eventually happen to the Milky Way itself. Their central black holes are generally dragged toward the new combined galaxy's center by gravity, eventually merging into one significantly larger black hole. Some of the largest supermassive black holes known, including the one imaged in the galaxy M87, may owe at least part of their extreme mass to a long history of exactly this kind of repeated merging. Black holes growing not only by slowly swallowing gas and stars over time, but by periodically absorbing entire other black holes brought in by galactic collisions. Seen against that much wider backdrop, Sagittarius A* stops looking like an isolated oddity and starts looking like a fairly ordinary, if unusually well-studied, example of what appears to be a near-universal feature of large galaxies. What makes it worth an entire episode's attention is not that it is special among black holes. It is that its proximity has allowed something no other black hole in the universe currently permits. Watching an individual star, again and again, complete real orbits close enough to test the deepest predictions of modern physics directly, rather than merely inferring an average mass from a statistical blur of distant starlight. What began as a stray hiss of radio static disrupting transatlantic phone calls in 1932 has become, across 9 decades of patient observation, one of the most thoroughly tested predictions in all of physics. Nobody who first heard that static could have guessed it traced back to a black hole 4 million times the mass of the Sun, let alone that the proof would eventually come not from any single grand discovery but from the accumulated, decades-long tracking of a handful of individual stars, watched year after year as they swung around a patch of sky that looked, for most of that time, completely and stubbornly empty. Radio astronomy located the object. Infrared tracking of stars like S2 weighed it, using nothing more exotic than Kepler's centuries-old orbital laws. S2's own closest approach in 2018 tested Einstein's predictions directly for the first time in this environment, and passed. The discovery of faster, tighter orbits like S4749's pushed that same test into an even more extreme regime, close enough to the black hole to reach 8% of the speed of light, and general relativity kept holding. A global network of radio telescopes, working together as one Earth-sized instrument, finally produced a direct image of the shadow those orbits had long predicted, confirming visually what decades of indirect tracking had already established. And running underneath all of it, the same honest uncertainty persists about what actually lies past the event horizon, a genuine, unresolved question at the frontier of physics, rather than a settled fact anyone is pretending to know. New instruments are already being built to push this same technique further. An enormous telescope currently under construction in Chile, called the Extremely Large Telescope, and an upgraded version of the gravity instrument that first confirmed S2's gravitational redshift, are being designed specifically to find fainter, closer, faster stars than any confirmed so far, testing general relativity in conditions even more extreme than S4714's 8% of light speed allows today. Some astronomers hope these instruments might eventually catch a star orbiting close enough and fast enough to reveal effects general relativity has not yet been tested against at all, effects that might finally start to show where the theory's limits genuinely lie, or effects that might simply confirm once again that Einstein's century-old mathematics continues to describe the universe correctly, even here, at the ragged edge of what nature allows a star to survive. What makes this particular pursuit worth the decades of patient effort is not simply the satisfaction of confirming a famous theory again and again, though that satisfaction is real. It is what the pursuit reveals about how science actually reaches its most extraordinary conclusions. Not through a single dramatic breakthrough, but through the accumulation of small, careful, independently repeated measurements, each one checking the last, each new star adding one more data point to a picture built up slowly enough that by the time the full shape of it becomes clear, it has already been tested from more angles than almost anyone would have thought necessary. A star catalogued as S4714, tracked patiently enough by patient people using patient instruments, turned out to be one of the sharpest tools available anywhere in the universe for testing whether gravity itself behaves the way the best equations available say it should. It does, so far, every single time it has been checked. Somewhere above the horizon tonight, whether or not the sky happens to be dark enough to see it, that same faint point of light is still tracing its 12-year loop, falling toward the edge of an object with no light of its own, and swinging back out again exactly on schedule, exactly as gravity says it must. The radio hiss, the tracked stars, the red-shifted light, the direct image of a shadow, all of it points back to the same single fact. At the center of the galaxy holding our own sun and Earth, an object with no surface and no light of its own is bending space and time exactly as Einstein's mathematics said it would, and one small fast star has become the sharpest available proof of it. S471 will keep completing its 12-year loop, diving to 8% of the speed of light and swinging back out again, long after every telescope currently watching it has been replaced by something better, and long after everyone reading these numbers today is gone. The Milky Way's own black hole is, by cosmic standards, an unremarkable one, a middling example of something astronomers now suspect sits at the heart of nearly every large galaxy in the observable universe. Tens of billions of them, most too distant and too faint for any star near their centers to ever be individually tracked the way S2 and S474 have been. Proximity, not uniqueness, is what makes this particular black hole special. It happens to be close enough, at a mere 26,000 light-years, for a handful of individual stars to be caught, one frame at a time over decades, tracing their own gravitational proof of concept in real time. Every large-scale theory of gravity ever proposed has eventually been tested against extreme conditions somewhere, and passed or failed there. General relativity has now been tested here, repeatedly, at the edge of an actual black hole, using nothing more than patient light collected from an ordinary-looking point in a mostly ordinary patch of sky. It has not failed yet. Whatever the next star found orbiting a little closer, a little faster eventually reveals that quiet, decades-long test is still running right now at the center of the only galaxy any of us has ever called home.